What do Martian dust devils? Protoplanetary disks where planets are formed. Volcanic lightning. Dusty astronauts. And aerosols traveling across oceans all have in common. In all of these situations, oxide particles collide repeatedly and, as a result, charge electrically. This is contact electrification. But why it occurs at all is still a mystery, especially in systems like these, where the colliding particles are all made from the same material. To study this, we use acoustic levitation, allowing us to isolate a single oxide sphere with ultrasound. We can bounce that sphere on a target plate in order to charge it. Look closely. Ready? This might have been too fast to see, so let's slow it down using a high-speed camera. Both the sphere and plate are made of silicon oxide. When we turn off the field, the sphere falls, bounces off the plate, then we catch it again using ultrasound. Through this collision, the sphere gained a tiny bit of electric charge. But how do we measure it? First, we apply an electric field and look at the response. The equation of motion is equivalent to a driven, damped harmonic oscillator. We fit the force expressions on the acceleration data and extract the charge. We can now repeat these operations: bounce, measure, then bounce, then measure, and obtain the charging behavior for a given pair. This sphere charged positive, and this next one charged negative. If we repeat this for many samples, we see that about 50% charge positive and 50% charge negative. Paradoxically, this tells us that each sample behaves almost as a different material. How can this be? The answer lies in what's on the surface of the samples. Even in the cleanest environments, tiny amounts of carbon compounds adsorb on the surface. We have found that if we remove these compounds from a sample using heat or plasma, we can control the charging, to the point where we can reverse the charging polarity in both directions. This even works between samples made of different oxides, to the point where we can reverse the natural tendency to charge more positive or more negative. However, if we just wait a few hours, the carbon comes back, and the effect on charging relaxes. Importantly, things don't quite revert to how they were before, as the surface carbon is not in equilibrium. This demonstrates the importance of the sample's history. Slight differences in conditions can lead to completely different outcomes. Ultimately, our results showed that differences in adsorbed carbon are what causes same material oxide particles to exchange charge. In settings ranging from lunar dust to volcanic plumes, we have finally identified the symmetry breaking parameter responsible for contact electrification.